Now that we understand the basics of vectors, the next major mathematical tool we need to learn is about the matrix. And we can define a matrix as a rectangular grid or table of ordered numbers. We usually write matrices with square brackets around a block of numbers with both rows and columns. So it might look something like this: a top row of 1 and 0, and then a bottom row of 2 and 3. Each entry in the matrix is called a component, just like with vectors. The size of a matrix is described by its two dimensions, so the numbers of rows and columns. So our example with 2 rows and 2 columns would be called a 2 by 2 matrix. You can have matrices of almost any size, like a 3 by 3 or 4 by 2, but for now we'll mostly be sticking to the 2 by 2 format. If you think about it, the vectors we learned about earlier are just special single column matrices. Before we do anything crazy, let's figure out how basic matrix math works. We can add matrices together by adding each of their matching components together one by one, exactly like we did with vectors. So let's say, for example, I wanted to add together two 2 by 2 matrices. The first matrix has a top row of 2 and 1 and a bottom row of 3 and 4. The second matrix has a top row of 1 and 0 and then a bottom row of 2 and 1. The first step would be to write them next to each other and then go component by component, matching the exact same spots. For the top left, 2 plus 1 is 3. For the top right, 1 plus 0 is 1. For the bottom left, 3 plus 2 is 5. And for the bottom right, 4 plus 1 is 5. Which means that our final matrix has a top row of 3 and 1, and then a bottom row of 5 and 5. And subtraction works the exact same way, just subtract the matching components. One quick note here is that just like vectors, if you want to add or subtract matrices, they have to have the exact same dimensions. You can't add a 2 by 2 matrix to a 3 by 3 matrix, or even a 2 by 2 matrix to a 2 by 3 matrix, because the components just won't match up. We can also multiply matrices by regular numbers or scalars, like we talked about last time. Let's pick a scalar, say 3, and multiply it by a 2 by 2 matrix with a top row of 1 and 2, and a bottom row of 0 and 4. We would just multiply every single component inside the matrix by 3. Our new matrix becomes 3 and 6 on the top and 0 and 12 on the bottom. The idea here is exactly the same as vector scalar multiplication. Now we can move on to a slightly trickier part, multiplying a matrix by a vector. Unlike addition, we don't just multiply component by component. Instead, we use something called the row by column method. Let's say we have a matrix with a top row of 0 and 1, and then a bottom row of 1 and 0. And let's also suppose that we want to multiply it by the vector 1, 0, so pretty simple example. To get the top component of our new vector, we multiply the first row of the matrix by the column of the vector. We match the first numbers and second numbers, so we do 0 times 1 plus 1 times 0. That equals 0, and we'll write it to the side here. To get the bottom component of the new vector, we multiply the second row of the matrix by the column of the vector. So 1 times 1 plus 0 times 0. That equals 1. So our starting vector was 1, 0, but after being multiplied by the matrix, our final vector should be 0, 1. The matrix has thus changed our vector's values. As we move forward, there are two other really important tools that we're going to be using all the time. The first is a very special type of matrix called the identity matrix. Think about the number 1 in regular math. If you multiply any number by 1, it stays exactly the same. The identity matrix is the matrix version of the number 1. The identity matrix is always a square matrix, meaning that it has an equal number of rows and columns, and it always has 1s on the diagonal going from top left to bottom right, and 0s everywhere else. So for example, the 2 by 2 identity matrix has a top row of 1, 0 and a bottom row of 0, 1. If you multiply any vector by the identity matrix, the vector will not change at all. If you want to check this for yourself, I encourage you all to pause the video and try it out. And the second tool which we frequently use is multiplying two matrices together. Sometimes you want to apply multiple transformations in a row. Instead of multiplying a vector by just one matrix and then doing it to another matrix and then another after that, we can actually multiply the matrices together first to create what we call a master matrix. We do this using the exact same row by column method we just learned, taking the rows of the first matrix and multiplying them against the columns of the second matrix one by one. And to end off this lesson, let's do a quick practice problem to make sure we've got the hang of it. Given a 2 by 2 matrix A with a top row of 2, 0 and a bottom row of 1, 3, let's apply it to a vector v, which is 2, 1. If you want to give this problem a try, then please pause the video and try it yourself. Okay, so let's go ahead and start the solution. We want to find the new vector by multiplying matrix A by vector v using the row by column method. First, let's find the top component of our new vector. We take the top row of our matrix, which is 2, 0, then we match it with our vector, which is 2 and 1. So we first multiply the first part, so 2 times 2 is 4, and then we multiply the second part, so 0 times 1 is 0. Then we can add these. 4 plus 0 is 4, so our top component of the final vector should be 4. Next, we can look at the bottom row of the matrix, which is 1 and 3. So again, we should match it with our vector 2, 1. We know that 1 times 2 is 2, and 3 times 1 is 3. So adding these together, we get 2 plus 3 is 5. So our bottom component for the final vector should be 5. Putting it all together, our final resulting vector is 4, 5. So that's it for matrices, and I'll see you in the next video.